So hi everyone. So let's continue with the heating property. The expander heating property. So the claim about the expander heating property is that it's even a lemma. It says that if you have a set, I don't remember the name, perhaps like B for Ben. I want to avoid this set. Well, V is the there is a graph of there is some graph. I think of it as a irregular graph. I also think of it as having small omega. All larger graphs on a spectral expander. But if you take a subset of the vertices and you take a random walk in this graph, so the first vertex is chosen uniformly at random, and every other vertex is chosen uniformly at random from the vertex set, from the neighbor set of the previous vertex, then what we claim is the probability that the random walk, say length t random walk, length t in vertices, that all of these vertices lie in B is at most, okay. So the best thing you can hope for is like the density of B, which we call mu, to the T. But what we'll prove is this thing where this is the density of B. Just number of vertices B normalized. Okay, so kind of you see the first step is optimal in a sense, which corresponds to the fact that V1 is chosen from a random, and then any other step, you get what you want, but there is some additive cost. And notice it's really important. This is we live in a good world. A bad world would have been if it would look something like this. I mean that result also that result is bad. That you want the omega to sit inside the T, so that as long as omega and u are together, so their sum is smaller than 1, you get an exponential decay in T. Here you don't have. So that's really crucial to have it. It's a good thing. And the proof, which we started last time, as almost any proof when you talk about spectral graph theory, particularly expanders, you want to relate the quantity that you're trying to understand, to bound, with some operator. So it's a number. So you want some operator that, from which you deduce this number. So in our case, what we saw last time is that this expression, and so this is the one vectors, but here I'm writing whether the normalization it has. Every entry is 1 over m, every entry is 1, so I don't write it. So you should think of it as the uniform distribution, and then you zero out the vertices, which are not in B. You can understand, zero out the vertices you reach to, and collect all the results. That's what we have here. And last time we actually showed formally, that this is exactly that for the case of a length 2 animal. That's what we called it U and B last time, but other. Stop. But intuitively, it takes a little bit of time to get used to it, but intuitively, at some point you don't move these things all over again. You kind of just see what happens. So you take a uniform step, and then I think of the vertices and labels. But then there is something which is not probabilistic. You can zero out vertices, the information in vertices. It is a zero here. So the way you would think about it sometimes is that you take a random step and then zero out, like vanish all the vertices outside it. And then you take a random step and then kind of again do that. But what do you mean take a random step? So what happens to these? So that's what we did last time. Eventually, at some point, you will kind of convince yourself that you understand this without doing the calculation. Hopefully. Okay. So that's the length 2 walk. What about the length 3 walk? How much? Exactly. So in general, maybe let's call this thing little b for below the 9. So little b is exactly as what we did before. So you start uniform, and then you do a p step, then you take a random. So it's not a p step, it's like a p, then you take a random step, and then do a p, and then take a random step, and so forth. So I should write like many pw's here, so I just do it like that. And it should be t minus 1, because I want to have TPs. That's 1. For example, here, I should have like 1 PW, not 2. Okay, so this is the claim. Technically, you prove it by induction, but you can do that. You can find it in the book that is linked. The site, I think, should link it of Salim. But even when you see the proof, it basically says you don't know. But I hope that once we did that, you're comfortable with it. Just remind us while we move right to the left, what we have the PW already. A uniform set of P. Then I have many of those. So this is one step, another step. But don't you advance to the left? Why do we always vote like okay. So it's just because right. So you have like when you start doing linear algebra or any course, and you have to make a choice and then stay consistent with it. Not everyone will be consistent as well. With regards to whether you multiply the matrix from the left or from the right. And we always do like multiply the vector. We put it to the right of the matrix, and so we need to. Okay. So this is the first operator that needs the input and then the second. Okay, so we want to bound P. We didn't even do it for the case of 2. We just showed the direction of 2. But we just do it for general activity. So we want to bound this quantity. And we call it Q1. Okay. Okay. So look at this thing. You say, how should I bound this? You know that the P you can almost see the P will give you the news, and the W should give you the omega, but it's not clear exactly how it works. Okay, so what we'll do, let's call this vertex V, not vertex, sorry, this vector V. For a second. We're just going to start peeling off this information. So here we have like an inner product between the all ones vector, a normalized all one vector, and V. And so what, if you have vectors which you don't really understand, so this vector you cannot understand, but that vector gives you the information of the vertices at the end, you don't really understand it. So if you have an inner product between two vectors which you don't understand the relations so well, what do you do essentially? You want to you don't understand the relations between them, so you're not going to count on the relations, unless you want to be really smart, but it's kind of optimal set. And so you just want to, understand them separately. Right? Because you don't want to understand the relations between one. And if you have an inner product, the way to say, well, I don't want to understand the relations. The inner product is the relation. You just use exactly the Cauchy-Schwarz. It tells you, I don't know what's going on here. I have two vectors. This says the angle between them. I don't know what's going on. I'm just going to use Cauchy-Schwarz, which bounds the angle by the individual nodes. Right? So, but when you see Cauchy-Schwarz, you should understand that someone made a compromise. He said, I don't get what's going on here. So you use Cauchy-Schwarz. So what I want to write is something like that. Everything is the true norm. Right? Do you remember the Cauchy-Schwarz? So, now, particular case, you have vectors. Cauchy-Schwarz is in general in the product spaces, but if you have the L2 norm, the Cauchy-Schwarz says that if you look at the inner product, think of this as numbers, complex, real numbers, whatever. So this is the inner product between the vector A and the vector B. So that's the smallest, even in absolute value, but the norm A, like the L2 norm of A, times the L2 norm of B. Okay. And you see here, you don't really have to understand anything about the relations. Now, if you're going to, having said that, if you're going to proceed with the proof as like that, you turns out you get a square root of mu here, not mu, which is slightly worse. So actually, there is something which you know about this inner product. So it's worth doing something before doing like the naive, like the off-the-shelf Cauchy-Schwarz. So to see that, I'm going to fix that a little bit. So that's true. I'm going to do something better. Just wanted to highlight the fact that Cauchy-Schwarz is used because of that, and usually you don't know anything, but here you know something. So we actually bound it. So you have here the sum of one I don't know, vi. I got the product between these two. I don't know how I wrote one I, it's just one. But you know something about vi at least. So because of the last p here, zeroes out everything outside of b, you know that vi is actually supported only on b. Right? So you don't really have to take this sum. This sum is an overkill. It has like many zeros there, which you're not accounting for to that. So actually, it's better. It's true, but it's the same, right? Let's call it okay, I and B. Yeah. Right, because the VI is outside of B or zero because of the last P here, which zeroes out anything which is outside of B. And now you can do Cauchy-Schwarz, but now the vectors are smaller. Now only supported on B rather than one and all the vertices. So really what we get from that, so this is kind of a story that I wanted to tell you, because I didn't want just like the inequality and what learn nothing from it. And then we took a bit more. Anyhow, now you should use Cauchy-Schwarz after you use some information about the V's, not really the relation between the V and one, but the V's. And then that's at most, you can imagine a one here. So you get the norm of the fourth vector times the norm of the second vector, which is just ones, but it's only v ones rather than v ones. And this thing, what is that? Square root of v. Square root of v, right? Oh, this is square root of v. I wanted to do something before I move there. It's too late. So this is square root of v. I'll manage. This is square root of v, and this is the norm of v. So to bound p, so to recap, p is at most the norm, the number of vertices in this square root times the L2 norm of v. Not squared, like that. Right? So okay, so let's look at v now. I mean, let's see what happens here. So v, this is a vector which you apply like many operators on this vector. And again, I don't really understand what happens after every PW, so I want to analyze it separately. So what do I mean? So V, well, it's the norm of this operator. Just copy V. Now, let me treat this as a vector. That's a choice, smart choice. I could have taken this vector, I could have taken this vector. So I'm looking at this operator, apply to this vector. Okay? If you do it like in the standard way, you take this operator, but that vector, you lose again some. Slightly careful, it's a slightly subtle proof. So look at this operator applied to that vector, and what do you know? You know that this thing is at most, kind of by the definition of the operator norm, this thing. Right, in general, if you have a vector, if you have some matrix A times some vector psi, and you look at the L2 norms, then this is most the norm of the operator, it's kind of the induced term, right? I mean, the definition of that is the maximum over all these conditions. Right? But the operator norm is defined in a way that it is induced from the original norm of the vector space by just taking the max over the ratios. So that certainly holds. That's the definition of this thing. And here my psi is this thing, and my A is this PW to the T minus 1. Okay. So again, this proof actually branches. You could make other choices, and then you wouldn't get the exact result. And I'm telling you that because I didn't know the proof. So I kind of tried to get it, and I got like square root of news everywhere. And then it hit me that you need to be really careful. You should have just opened the book. Okay, anyway, that's. So good. So when you have a norm of vector space, say the 2 norm, then you immediately get what's called the operator norm. It's induced from that. And the norm for matrix is precisely the maximum over all x in all vectors, maybe non-zero vectors. It's well, these are the norms vectors. Right, so it really asks what is the maximum stretch of A. Right? So you should take that if you have so you should take the largest eigenvalue, the eigenvector correspond to the largest eigenvalue in absolute value. That's what it is really. But we actually used this last time, right? We talked about this when this is D in our matrix. Like the yes, okay. So for the matrix A, the unnormalized matrix is D. For the normalized matrix W, it's 1, because W is just 1 over D times A. Right, so in our case, in our A, if this is like an adjacency matrix of a D-regular graph, then this is just D. So, it's okay. It's also like the maximum between lambda 1 and it's the worst one between lambda 1 and the last one. And this is D, and I told you that this is most D, so that's why it's D. But if you take W, then W is like 1 over D times N. It's the random walk matrix. We normalize. So this is, scalars get out of the norm. So the matrix norm of this thing is 1. But this is not what we're looking at. We're looking at PW. It's another. Yes, good. It's really important. Good. So not every norm is multiplicative, but every norm which is every norm on operators which is induced by norms of vectors is multiplicative, which means, and we'll use it in a second, that this holds. So for 2 matrices, for 2 operators, this holds. Subadditivity is always true. It's kind of by the definition of norm. So the norm of vectors is at most the sum of the norms, but submultiplicativity is not a general property of norms, but it is a consequence of the norm being induced. Really easy to do. So that's called submultiplicativity, which we'll use in a second. Okay, so maybe it should be clear. So here, so this is like this is different. This is a different norm than those. This is a norm of operators, and all of the rest of norm over vectors. But it's the induced norm. And you see, because it's defined as the max, we know that that's true. Right? Because the norm of this thing is defined as the maximum over all, applying it to any vector divided by the vector norm. In particular, it holds with inequality on that particular vector. It's really useful, the fact that you can relate, of course, the operator norm of the vectors. So is it clear? Any questions? And just in general about norms and matrices, life. Okay. So we have to analyze this thing and that. Let's start with this maybe. The one, the vector norm. So, okay, so that's, I can just see what this, so that's a vector. You can just look at the vector. So what is this vector? So, right, so P is like is this matrix that has 1 at the diagonal corresponding to vertices in B and 0 otherwise. That's P, that's how we defined it last time. So these are the B vertices, and this is the rest of the vertices. And of course, 0 otherwise. It's just a block matrix. Diagonal blocks 1 and 0. So when you apply it to this vector, even before the node, just this vector, right? This is the one vector normalized. You have like 1 over n everywhere. So what would you get? 1 over n, 1, another one. Exactly. So in the B part, you get this, and in the rest, you get zeros. And then you can actually just easily compute the norm of this thing, right? So because of that, the norm of P1, so let's just write it like formally. Don't get a mistake here. Right, so you have this thing that's generally regardless of what the vector is. But now we know that you have B summands that give you 1 over n squared, and 0 otherwise. Right, so B of the summands give you 1 over n squared. It's square root outside. You see, it's not really nice because I forgot to normalize it. I should have changed a little bit the equation, but anyhow, let's continue with that. I don't want to. But anyhow, this give you, so B over n is a mu. You have a square root of mu, and then you have like another weirdly square root. B over n is a mu inside square. So I think we're going to take B over n and 1 over n. That's good. I mean, actually, it's really good. You see, this looks ugly as units. Like this doesn't have units, and this has units. You get what I say? It's not a density. Okay, exactly. Good. Okay, so P, so let's just recollect our thoughts here. So to recap, P is at most. So we had where is the square root of B, which if I would have in a better way, you wouldn't have it. You have it here. And then you have these two things we're trying to bound. The norm of the operator and this thing. This thing gives you that. And then you have the norm of the operator, which is like the most interesting. Right? But then you see, this is another square root of it. So you get mu, which is what is promised to us, times the norm of this operator, which is good. Because we know that at the end, the bound should be mu times mu plus omega to the t minus 1. Wait, oops, okay. So let's bound the operator with this matrix. Right, so W has operator number 1. PW has definitely to the t minus 1 has different norm. Just new, or now is it not again? Okay, fair enough. All simple, right? It's not fair. It's not a good comparison. Okay, so how would you bound the norm of this vector? So there are two kind of, how do you say it in English? Schools, two schools for that. Me and two other students and the rest. More. So the rest of the world is doing the following. The rest of the world is smart. So he says, I don't understand the relation between this. I mean, one PW I can understand, you can actually write it down and understand what's going on. Many PWs, it's like, well, it depends on the graph structure, SLB. So they say, again, I'm just going to use the sub-multiplicativity. Leave me alone. Just going to use that. And then I only have to bound the operator norm of PW. And let's go with the usual school. The more advanced school try to understand it. In this case, it won't really help you because general, you can say interesting things about relations. But anyhow, this is something you will see all the time. Again, it corresponds to the fact, I want you guys to understand why we're doing things. It corresponds to the fact that you want to bound an operator norm which you don't understand, but it's just the power of some operator which you have a better chance of understanding, so it's a good idea to do that step. Analog to Cauchy-Schwarz. Okay, so and you actually know what we expect. We expect this to be bounded by mu plus omega. So how do you see that? So first of all, you can actually just write down the operator and look at its norm. It's not hard. It's a very simple operator. But I have a trick which is nice. In the book, there's another trick. I hope it's also my trick is also okay. So the norm has a really interesting property, maybe just in general. The norm of two matrices is the same if you kind of cycle V for the cyclic property. Sometimes called also the tracial property because the trace has this norm as well. But I feel like this property, but it feels like the norm has this property as well. So I attribute this to the trace. So it's called the cyclic property. And it also holds even if A and B are not of the same side, as long as it makes sense to multiply them. Right, so for example, maybe A and B were vectors. For an example, to make it clear, maybe A was like a, let's call it a little a. So maybe A was like a lane, like a row vector, which we wrote write like that because vectors are common vectors here. Oh, so maybe it's a row vector, sorry. And B is a column vector. That's a matrix, right? So what I'm saying is that the norm of this matrix, which is a matrix, it's a rank 1 matrix, it's the same as the norm of flipping B. But what is this quantity now? It's a scalar, right? It's a number. Which, by the way, the norm of a scalar is just the absolute value of it. So you see, a rank, for example, A and B don't have to be of the same dimension. As long as you can multiply in both ways, it's fine. NM, as long as you can multiply it. So once this is NM, this is MN, and that gives you like a nice way to compute the operator norm of, say, rank 1 matrices easily. This is kind of the outer product, and this is the inner product. So in our case, it's actually almost, it's not exactly like that, but you can write it like that. So W, recall, is like 1 normalized. W is the whole 1 over n. So I can write it like that. Because if I take the outer product, a row times a column of the normalized nil to norm. The whole ones vector, I get W. W random. Yes, of course. So I'm ahead of myself for a second, okay? Sorry. There is one step missing. My bad. I forgot that. Yeah, anyhow, it doesn't matter. That's, yeah. So W we wrote as J times E, where J was actually, we wrote it, we arrived to J from the one transpose. So, and then from the subadditivity, which by the way holds for any norm, doesn't have to be induced, this holds. And then what I said should have been said. J, there are two summands, which actually makes sense, and it's a good direction, good step, because we want this to be bounded by mu plus omega. So this is going to be the mu, this is going to be the omega. And this thing is what I wanted to say. So Pj is P normalized like that. Oh, it's fine. And then you can cycle this vector here to get a number. Right? Because it will be like a number. And I don't even need the absolute value because it's positive or non-negative. Because everything here is. Yeah. And this you can easily compute. Actually, we almost did that. So p times 1 over 1 the square root of n we did something like that.
Well, you.
So it's actually mu, right?
So,
the outer one, the one, yeah, right, good. Right. So, yeah, so this is the vector that you get with 1 over square root of m. Right, p times this thing is like, this is like the, sorry, this thing is like the vector 1 over square root m and zeros, where this is in D, right? Here we did something similar. We have the 1 over n times p. Same thing, just you get 1 over the square root of n, is 1 over n d. And then when you take the product with this thing, which is always 1 over square root of n, you get 1 over n b times. Good. So this is mu. Well, mu. And this, so how can I bound this thing? I want to bound this by omega. That's the last thing I want to do, right? Once I do that, I'm done. So why is PE is at most omega? Do you understand the relation between P and E? We don't. Who knows? P is the error vector of the graph. P is the set, encodes the set. But we can always use the sum multiplicativity because we don't understand the old school. But that's fine, right? The norm of P is 1. One, right? It's this matrix. It's essentially a projection matrix. And it has norm 1. It has only 1 and 0 as eigenvalues, for example, and the norm is like the max eigenvalue in absolute value. But you should also think it's a projection. It doesn't make something larger, only smaller. And it has no 1 because within the space it projects, so it actually does not cause any harm. It still has the same length. So you should think of, when I look at a norm, I think of all things together. Because sometimes other perspectives are useful. So the eigenvalues, or like what it does, about the eigenvalues. So this is one for all reasons, and this is by definition, right? It's bounded by omega. That's it. We're done, right? Apply it. I should just write it down, but we're done. This is a prototype of a proof in spectral graph theory.
What is this inequality of equality?
To be, it's actually inequality. But omega was defined to be the norm of E. So the reason I wrote inequality just to excuse the behavior is that usually you have a graph and you know a bound on the spectral expansion. So I kind of think of it as bound. But here I just wrote omega as the actual expansion. Good. So overall, we get the P, the probability that we want to bound. Over here, it's like a mu. And then you have, we bounded the operator norm of the power by the power of the operator norm. And PW, and the operator of PW is mu plus omega. Also slightly improve that and put a 1 minus omega here. But it doesn't really matter. Slightly better bound. It's not weird. I mean, it's still larger than mu to the t. Because it's a convex combination between mu and 1. But you can do that. But I think I'll remark later why is it. You can replace this 1 times mu by 1 minus omega times mu. Just sometimes it's useful.
These are 1. It's 1 minus omega plus omega?
No, only that. So what I'm saying is that's what we actually proved. And what you can prove, slightly better bound, is this. You're not doing just
okay.
Right. And the question isn't that weird because maybe it's smaller than mu to the t, You cannot be better than UD, but it's not because you can write it like that, and then you see it's a convex combination between U and 1, so it's still large when U is smaller than 1, right? So it's still a value. Anyhow, questions about that?